Okay, chemistry kids, today or this week, one of the lessons we're going to be focusing on is Visible Learning Objective 2-2, which covers the history of the atom. And so I'm going to take you through just a quick lesson on 2-2, and there might be some other assignments that your individual teachers might assign you that go along with this. But we're going to go through 2-2, go through all the facts you need to know, and maybe show you a couple of the different activities that you might be doing. And if you're not in class, these are things that you might need to complete at home. Okay, so again, it's 2-2, so let's pull up the Visible Learning document and check that out. Okay, so if we look at 2-2, really it's just atomic history. And so now that we know the basic structure of an atom, and we're talking about the very basics, so protons, neutrons in the nucleus is really small, it's positively charged, and it's dense because that's where all the mass is. And then on the outside, in the electron cloud or in orbitals or however you want to define it right now, we just know that the electrons are on the outside. Okay, so that's basically it. And the electrons take up most of the space of the atom, and most of the mass is in the very small centered dense nucleus. Okay, but we are kind of responsible in knowing how we got to this idea of an atom. And 2-2, our Visible Learning Objective, kind of takes us through the history of the different the people and the different experiments they did to lead us to our understanding of the atom. Okay, so there are guided notes that go along with this. So if you're at home and you want to fill out the guided notes, make sure you get a copy of those and print them out. And then also, there's a worksheet that you might be asked to do, and there's also a web activity that you can do. But that's going to just depend on what your teacher wants you to complete. Okay, so let's get into it. All right, so atomic history. All right, again, let's review our known idea of what an atom is. A very simple definition is we're going to say you have the nucleus in the middle. That's where the positive charge is and where the mass is. And then you have the electrons on the outside in the cloud. Okay, but how did we get to that idea? Okay, here's kind of a basic timeline. And notice there's a big jump. So way long time ago, Greek philosophers were thinking about this idea that if you kept breaking down an element or breaking down matter, you would eventually get to the smallest particle that you could no longer break down. And Democritus came up with this idea a long time ago, and people kind of thought about it. Then, there was a lot of time in history where we weren't really focusing on science that much. And then later on, as we get closer to our time, you have a bunch of scientists theorizing, but then also doing experiments to test those theories. And that's what we want to get into today. All right. So again, the starting point of the atom comes from the Greeks, and Democritus usually gets the credit for it. And the word he used was atomos, which just means indivisible. Okay. And so that's basically what if you see Democritus, the first guy to think of this idea of the smallest particle of matter. Okay. Then we skip forward in time, and you don't need to memorize the dates, but this was around 1800s, and Dalton comes up with his atomic theory. Okay, and you want to know those 5 tenets right there listed. But the main thing you want to know about Dalton is, just in his thought experiment, he was able to pretty much get everything right on the money, but he was wrong a couple places. But if you just tweak the argument, then he's kind of right. So let's look into that. So you can read through those tenets, but let's talk about where he was wrong, and what we need to correct. Okay, so the places where he went wrong is he said all atoms of the same element have to be identical. Okay, and we now know that that's not correct because we have different isotopes, right? We have carbon 12, we got carbon 13, we got carbon 14. So they're identical in terms of atomic number, but they're not necessarily identical in terms of mass. And we know that the differing in mass is the different number of neutrons. So he said all atoms of the same element were identical. He's a little bit wrong there, okay? And then he said atoms are indivisible. And we, just by discussing subatomic particles, remember subatomic means smaller than an atom. So we know atoms can be broken down further. So atoms are not indivisible, they are divisible, but they are the smallest unit of an element. Once you break an atom down further than into its subatomic particles, those subatomic particles by themselves no longer represent the element of the atom they make up. So, pretty close. Dalton's pretty close, okay? And then we have some experiments to understand what these atoms might look like, okay? So we have this idea of an atom now, but we don't really know what its structure might be, okay? So we have a couple of experiments that we want to know about, just general idea of what they did, and then also the conclusions they made, and the people that get credit for it, okay? So the first experiment is J.J. Thomson, okay, and his cathode ray tube experiment. The second one we're going to go over is the gold foil experiment, and that's Ernst Rutherford, which we'll talk about here in a second. And then there's one fun experiment. It's not really as important for us to know, like, let's say, for the SOL, but it is kind of a fun experiment and a pretty impressive experiment that Robert Millikan did in Chicago, and it's called the oil drop experiment. So we'll get into those. All right. So first, let's talk about the cathode ray tube experiment. Okay. So J.J. Thomson gets credited with discovering the electron. Now, he called them corpuscles that we now call the electron, but basically he figured out that there were negatively charged particles. Okay, and we now call those the electrons. And so he discovered these negatively charged particles that are in matter, okay, the electron, and he did it through what we call the cathode ray tube experiment. So we're going to kind of talk about what that means. But essentially was he had a beam go from positive to negative, and he wanted to know, what is that beam made up of, okay? What kind of particles is making up that beam? Okay, so as he fired the beam down the tube, okay, he decided to apply a magnetic field on either side of the tube, okay? And so now we have a positive here and a negative here. So as the beam goes this way, from negative to positive, if the particles are neutral, we would expect them to go straight through, okay, and not be affected by the magnetic field. But if they're charged, they're going to be affected by it. They're going to be repelled by the like charge, and they're going to be attracted to the opposite charge. So what happened was he shot the beam through with the magnetic field and noticed that the beam curved up towards the positive. So it was repelled by the negative and attracted to the positive. That means the beam itself must have been negative. So the particles in the beam were negatively charged, and he called those particles the electron. Okay? So from that, he came up with an incorrect theory of what an atom looks like, but he does get credited for discovering the negatively charged electron. Okay, so that's kind of cool. All right. So what you want to remember, J.J. Thomson, cathode ray, discovered the electron. You probably don't need to know the plum pudding model, but J.J. Thomson's incorrect model of an atom was called the plum pudding model. And he theorized that the atom was a cloud of positive charge with negatively charged particles just within that cloud randomly dispersed, and that's what he said an atom's structure was. Okay, so in comes Rutherford to kind of test that idea. He, obviously he read about J.J. Thomson's experiment, and he wanted to go test it to see if he could prove the plum pudding model correct. The thought was he kind of agreed with J.J. Thomson and wanted to kind of prove J.J. Thomson correct. But so he created this experiment called the gold foil experiment, and it actually proved J.J. Thomson's model wrong. Okay, so let's get into the gold foil experiment. Okay, so what he did was he took alpha particles, which are these products of nuclear decay, and we're gonna talk about nuclear radiation a little bit more when we get to 2-5 in our visible learning. But right now, you just need to know that he took these alpha particles that are positively charged. Okay, so alpha particles are positively charged, and he fired those positive charged particles at a sheet of gold foil. Okay, so you have the lead block with the uranium that is emitting alpha particles, the positively charged particles, and he's going to shoot those through this piece of gold foil and see what happens. And he set up the screen that would detect where the particles end up. So if they go straight through, all the particles would end up here. If they get bent, maybe they get curved up there or curved down there, we'd find out. Okay, so that's the idea. He's going to shoot positive charges through gold foil. And the reason why he chose gold foil is because they're only a few atoms thick. So essentially, he's firing these particles through a single atom, a layer of atoms, okay, essentially. So this is what he expected. If the plum pudding model was correct, he thought all the alpha particles would just go through, okay, kind of like that. Okay, but this is what he got. Okay, he fired them through, and a lot of them, most of them went through. Let's see if I can do this. Okay, so most of them went through, but a few of them kind of were bent. Their paths got bent. Some of them got redirected straight back. Okay, and so what must be going on there? Again, remember, this beam is full of positively charged particles. So to repel the particles, there must be something else that's positively charged doing that, right? Because we know like charges repel, okay? So what happens is you have the very small positive nucleus, and so if any of the lines were close to the nucleus, they would bend away. And sometimes they might bend way back, okay? So most of the particles went through because that positive nucleus, that's positive center of the atom, is very small. So most of the beams just kind of went straight through unaffected, but there were a few that were, okay? Whoops. All right, so I guess the main takeaway to take from the Rutherford experiment is Rutherford kind of figured out our basic idea of an atom, okay? The atom is mostly empty space, not really empty space, but it's mostly space where the electrons are, okay? And there's a small, dense, positive center, really, really small, okay? And so Rutherford gets kind of credited with discovering the nucleus, okay? And basically the overall structure of the atom, okay? And he proved J.J. Thomson's model wrong, okay? So just a fun experiment that was done to kind of actually calculate the charge of an electron was called the oil drop experiment. And so what happened is Robert Millikan took some oil and he put it through kind of the sprayer, this thing called an atomizer, and it made these little oil droplets, really tiny oil droplets. And then he shot X-rays at the oil droplets to knock electrons off, to make them become positively charged. So the X-rays get shot at the oil droplets, the electrons get shone off the oil drop, so that means the oil drop is overall positively charged. And then what he did was he had a magnetic plate, and now if you have negative or positively charged oil droplets, they're going to be repelled by the positive and attracted to the negative, and sometimes those oil drops would end up just hovering there, okay? So again, he would atomize the oil. He would shoot the X-ray through the oil. Okay, so the X-ray would go through, boom, and hit the oil drop and become positive. Okay, and then he put a charge on the electric plates, and what would happen is that oil droplet would be stuck between a positive plate here, and gravity would be pulling down, but it would be being repelled because they're both positively charged. And based on the amount of repulsion there, he was actually able to calculate the charge of an electron in coulombs. And I think he was within 1% of today's accepted value. So this was back in 1911, and it's pretty cool. I think 1909, sorry. And, you know, it's just a pretty fun experiment that he did. So you don't really need to know too much about the oil drop experiment, but just kind of put the names together. All right. So we define the charge of an electron as -1, but what it really is in coulombs is 1.609 times 10 to the -19 coulombs. And he was within 1% of the accepted value from his oil drop experiment, which is pretty cool. Okay. Pretty impressive. Okay. So what do we want to take from this? We want to know the names, we want to know the experiments and what they got credit for. But moving forward, we really want to understand the structure of an atom. And later on in Unit 3, we're going to focus mostly on the electrons because they're on what's on the outside. And when it comes to chemical reacting, when it comes to atoms bumping into other atoms, the electrons are the most important part to look at because it's the electrons that come in contact with each other. The nuclei don't really come in contact with each other because they're at the center and they're protected by this big cloud of electrons. So when two atoms bump into each other, it's really the electron clouds that are bumping into each other. And when things chemically react, it's the electrons that are in play. So when we get to Unit 3, we're going to focus mostly on the electron, but we want to have an idea of the basic size of the atom and the basic structure pertaining to the nucleus and the rest of the atom. So if you took a big football stadium and you said that was the size of an atom, the nucleus would be about the size of a marble. And that's how much smaller the nucleus is compared to the rest of the atom. But that is where essentially all the mass of the atom is. So pretty cool to think about. All right. So here are all the protons, neutrons, and electrons that we've been learning about already. We already know this stuff. You don't really need to know the actual mass of a proton in grams or a neutron in grams. You know, we'll just say it has a mass of 1, AMU, and we'll give we'll say an electron has 0 mass. Okay, but the things to take from this lesson are kind of the order in which we just discussed everything. The Greeks with the first idea of atomos, something that's indivisible. Then you got Dalton and his atomic theory. We want to know where he went wrong. Then we got J.J. Thomson, cathode ray. He discovered the electron. Rutherford, Goldfoil. He learns about the nucleus. And then we got Millikan, the oil drop experiment, and he is able to calculate the charge of an electron. Okay. There's other experiments and other scientists that can be named here. Here's a timeline. If you do a quick Google search on atomic theory or atomic theory history timeline, you can get a bunch of different ideas here, okay? But that's essentially what we need to know from 2-1. And again, your teacher will have other worksheets that you can do to help you, remember all of this information. But, this is the one time where chemistry class is going to be kind of like history class. You don't need to memorize the dates, but you do need to know some names and some experiments and the conclusions of those experiments. So again, the outline is here. If you know this stuff, you're in good shape for 2-2. Thanks for listening.